Today we're going to talk about section 3.7, the fundamental theorem of algebra. So you're going to be able to use the fundamental theorem of algebra to determine the number of solutions. And you're also going to be able to use Descartes' rule of sign to identify possible roots of polynomial equations. So the fundamental theorem of algebra states that if f of x is a polynomial of a degree n, where n is greater than 0, then you're going to have that many solutions. So if n is 2, then you will have 2 solutions. If n is 3, you will have 3 solutions, and so on. Descartes' rule of sign. Descartes was a French mathematician who found a relationship between the coefficients of polynomial functions and the number of positive and negative roots. So you're going to see that we are going to, in order to determine the positive real zeros, if we plug in x or leave x, we're going to take a look at what the signs are in between each of those variables or terms. The negative rule states that if we evaluate the function and plug in negative x, then we can look at how many sign changes we have to determine the negative roots. So what does that mean? Well, let's take a look at example 1. If we want to determine the possible number of positive real zeros, negative real zeros, and imaginary zeros, first we want to look at our largest exponent. So we know we have a possibility of 6 total solutions is what we need. We then want to take a look at our positive sign changes. So in front of this 6 is a positive x to the 6th power. So there is 1 sign change here, 2 sign changes, 3 sign changes, and that is it for our function. So positive sign changes, we have a total of 3. Negative sign changes, if we plug in f of negative x and evaluate that for our function, a negative to the 6th power will remain a positive. Negative to the 5th power will be a negative, and a negative times a negative gives us a positive. A negative raised to the 4th power will remain a positive. A negative raised to the 3rd power will be a negative, but a negative times a negative is a positive. A negative to the 2nd power is a positive, but a positive times a negative is a negative. Negative times a negative is a positive, and our constant remains a negative 8. So if we look at the number of sign changes here, we have 1, 2, 3 sign changes for our negative values. So we want to subtract 2 from this 3 to give us our other possible roots. So because we have conjugates, we always want to take into effect that we can subtract 2 from this. So we could also have a possibility of 1 positive, subtract 2 from 3, and we could have a possibility of 1 negative. So this column right here, the imaginary, we're going to fill in after the fact. So Descartes' rule only tells us the possible positives, so we said 3 and 1, and the possible negatives, we said 3 and 1 as well. We know the total because our highest value has to be 6. So we're going to say we could have a possibility of 3 positives, 3 negatives, which would leave us 3 plus 3 is 6, 0 imaginary. We could also have a possibility of 3 positives, 1 negative, 3 plus 1 is 4, and that would give us an imaginary number of 6 to get to our total. We could have a possibility of 1 positive and 3 negatives, which again, 1 plus 3 is 4, plus 2 more gives us our total of 6. Or we could have a possibility of 1 positive, 1 negative, which we would need to add 4 imaginary to equal 6. In this column right here, your imaginary column, you have to account for the conjugate pairs. So all of these numbers should be even numbers. If you are getting odd numbers in your imaginary column, you are doing something wrong. So these are the possible combinations of solutions that we can have. So let's take a look at this example. How many solutions do we have to have? Well, we have to have 5 solutions. So let's look at our sign changes. Put our plus for our positive 2. We go from a positive to a negative, negative to a positive, positive to a negative, negative to a positive. So my positive changes are a total of 4. My negative changes, so when you evaluate this for a negative to the 5th power is a negative times a positive remains a negative. If you evaluate this for negative x to the 4th, it would become a positive times a negative will remain a negative. Negative x to the 3rd power would be a negative times a negative is a positive. Negative x to the 2nd power would be a positive, so that remains a positive. A negative x times a negative changes to a positive, and our constant stays the same. So we only have 1 sign change when we evaluate that for the negative. So now we need to fill in our chart. If we have 4 possible positives and 1 negative, our combination equals 5, so we have 0 imaginary. Remember, you need to subtract 2 each time, so we could also have a combination of 2 positives, 1 negative, which would leave us 2 imaginary, so our positives could be 4, 2, or 0. We could have 0 positives, 1 negative, and that would leave us 4 imaginary. So all of our totals equal 5. Our imaginary column is all even numbers. So these are the different combinations of possible solutions we could have. So now let's take it a step further and let's actually find all the roots of the polynomial equation using our P's and Q's and then using Descartes' rule of sign. So when we take our P's and put them over our Q's for our possible rational roots, the factors of 4 are 1, 2, and 4. Factors of 1 are 1, so our possible roots are plus or minus 1, plus or minus 2, plus or minus 4. When we look at Descartes' rule of signs, to look at our positive values, we say there's 1 change, 2 change, 3 sign changes. Remember, we can subtract 2 from that, so it can be 3 or 1. Our negative possibilities are negative to the 3rd power is a negative. Negative squared is a positive times a negative is a negative. Negative times a positive is a negative, and we have a negative 4. There are 0 sign changes. So when we list out our table for our positives, our negatives, and our imaginaries, we know we have to have a total of 3. So we can have 3 positives, 0 negatives, 0 imaginary would give us our total of 3. We could also have 1 positive, 0 negatives, which mean we could have a combination of 2 imaginary. So 3, 0, and 1, 0 are our only combinations we can have. Now we need to use our synthetic division to solve. So 1, negative 4, positive 6, negative 4. I know I can have 3 positive and no negative solutions. So in my possible zeros, I can just eliminate all of my negative possibilities. So then I want to give 2 a try. Drop your first term, multiply, add, multiply, add, multiply, add. You get 0 as your remainder, so you know 2 is a root or a solution. So I'm going to go ahead and just put my 2 over here. Because we were working with a cubic, I know now that I have a quadratic, so I can plug this in to my quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. When I simplify this, I get 2 plus or minus the square root of negative 4 over 2. I know I have an imaginary number, which right here it said 1 possible, 2 imaginary, so that's the combination we're going to have. The square root of negative 4 is 2 plus or minus 2i over 2. Our heart is complete. They are all divisible by 2. So we get x is equal to 1 plus or minus I. So our other roots are 1 plus I and 1 minus I. And we have our 3 roots of our polynomial. So let's take a look at another one. Looking at example 5, if we list our p's over our q's for our possible roots, we get plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16. When we do our positives and our negatives, 1, 2, 3, I have 3 positive sign changes. When you subtract 2, you can get a 1. When we look at our negative sign changes, I have a negative. Negative times a positive is a negative. Positive. Positive. Negative times a negative is a positive and a negative. So I have 2 negative changes. 2 minus 2 is 0. So my possibilities are for my plus, my minus, or my imaginary combinations. I can have 3, 2, which equals 5 total, so our imaginary is 0. I can have 3, 0, which would leave our imaginary to be 2. Then I want to pair my 1. I can have 1, 2, which means we would have 2 imaginary, or I can have 1, 0, which would leave me 4 imaginaries, are my possible combinations. Then when we use our synthetic division, your coefficients of your terms, 8, negative 16. I'm going to try a negative 1 first so that I start small. Drop your first term, multiply, add, multiply, add, multiply, add, multiply, add, multiply. Got a remainder of 0, so I know one of my roots is negative 1. Continue with my synthetic division because this is now to the 4th power. So I'm going to try a positive 2. Drop your first term, multiply, add, multiply, add, multiply, add, multiply, add. Again, it worked. Another root is positive 2. I'm going to try my synthetic division another time because we're only to a cubic. Drop your first term, multiply, add, multiply, add, multiply, add. It worked again, so I'm an amazing guesser. I have 3 real, or I have 2 negative, 1 positive, so my last 2 are imaginary. When I plug this into the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. I get x is equal to 2 plus or minus the square root of negative 12. When I simplify all of my pieces, I know that that's an imaginary number, so x, when you simplify the square root of negative 12i, is plus or minus 2i root 3 all over 2. My heart is complete, so I can divide all of those by 2. So I know x is equal to 1 plus or minus I root 3. So my last 2 solutions are 1 plus I root 3 and 1, its conjugate, minus I root 3.